In the past two lectures, we saw an introduction to clause methods and then unification, the basis of first-order resolution. So with this one slide, we're able to put all of that together and finally see the resolution rule as it's used in first-order logic. Now, we have seen this rule before a couple of lectures ago, and there's actually only one change in it. So you may recall from before we had two clauses, and before they had complementary literals, so be here, not be here, they would cancel out, if you like, and we would be left with all the remaining literals. The only difference is now we allow unification to make two literals complementary that perhaps weren't. So we have B and not D, and we only need B and D to be unifiable, which we write as B sigma equals D sigma. So sigma is the unifier, and the result is as before, except we apply sigma to the other literals. Now this is as I hinted last time when talking about unification. So we immediately think of the common instance of the two literals, but what we really need is the substitution that makes them the same, because we need the substitution elsewhere. Of course, in a real implementation, you're not going to create substitutions. You're going to update pointers in some clever way, and the instantiation of these literals, so the plugging in of terms for the variables, will happen much more efficiently than the kind of copying which is suggested here. Now this remark here that sigma is a most general unifier, I should say something about. Now I don't want to get distracted and go into the theory of unification, which, believe me, there is quite a lot of it, and just say that a most general unifier is a really obvious thing. So as I have in this example near the bottom of the slide, let's say we want to unify these two terms here, fxy, faz. So x is a variable, and so x has to be instantiated with a. Y and z are both variables, and it turns out we can choose. We can set y to z or z to y. So in fact, unification is unique only up to such variable renamings. So these two solutions, fay and faz, are essentially equivalent, and they are both the result of a most general unification. But what if we did something like FAA? Here we would be pointlessly updating y and z to be a, or maybe to be some other term like 3 or g of x or any such thing. It's clearly pointless, arbitrary, and results in something which is less useful, because the more variables we have left in our clauses, the more general and expressive they are. Luckily, we don't need to go to any extra trouble to get most general unifiers. Any algorithm that isn't actually stupid will give you those. Now, I have said this already, but it's worth stressing. Variables in a clause are local to it. So when we see down here these two clauses, p of x and not p of g of x, this x is local to this clause, this x is local to this clause. We have the right to rename either copy of x to any variable we like, and our renaming has to be consistent only within that particular clause. So in particular, if there were other literals here containing x, of course they would all have to be renamed. but occurrences of X in other clauses are independent. It's necessary to rename the variables prior to resolution because otherwise, and you could actually see quite quickly in some of our examples, you would start to get name clashes very quickly. So if you are asked to resolve these two clauses, it would be wrong to say it's impossible because of an occurs check. So it is true that is P of X, and this is not P of G of X. So if you were to directly try to unify them, you would indeed get an occurs check error. But you would be wrong because you have forgotten that before you even get involved with unification, so when you're still at the level of resolution, you should make sure that the variables in these two clauses do not overlap. In a real theorem prover, this is done simply by using a counter that keeps ticking upwards. It turns out that the resolution rule by itself is not enough. The problem is that we are trying to get the empty clause, but resolution steps tend to make clauses longer. If you are good at maths, you'll figure out that if each clause has at least two literals, then the result of resolution, that clause will also have at least two literals. And so we have no hope of getting down to even a one literal clause, let alone the empty clause. There is one thing that can help a bit. Our clauses are sets, so if you get a clause such as PPQ with the literal P repeated, it's a set, so we can suppress the duplicate, and that gives us a shorter clause. It turns out we need something stronger than that. We need to aggressively be able to squash similar looking literals down to a single one. We do this with an inference rule called factoring. What you see here is a clause that has some literals b1 up to bk, which are perhaps not identical, but they are unifiable. There is a single substitution, sigma, that makes all of these literals the same. What we can then do by this factoring inference is to collapse them down to a single copy, some b, which, because we have applied this substitution sigma, all of those literals b1 up to bk all collapse down to this b1. As for the remaining literals, you have to apply sigma to those as well. The idea is simply, if you like, we applied sigma to this clause in the beginning, and then we duplicated the literals in the set. It turns out that if we have resolution and factoring together, that combination is complete for first-order logic. Complete, remember, means that every valid formula will eventually be proved. Of course, you may need to wait a very long time, and you may need to buy a lot of memory, but at least it will be proved. Here's an example. I'd like to call it a literal example, and I suppose it is little, but allow me to tell you that this actually is quite a tricky problem. This is not the sort of problem that you can eyeball and say, yeah, that is a theorem. I wish I could now go to the other projector and try and turn this wretched thing into clauses before you in front of your eyes. I'm afraid I can't. Let me just mention, though, there are tricks for negating if and only if and turning it into clauses. So you might consider that if and only if is a conjunction, that is, it's this implies that, and that implies this. It is a conjunction, but when you're negating it, the negation of an if and only if is equivalent to having the if and only if of either of those guys negated. So there are lots of ways of simplifying this thing. Of course, you mustn't forget to negate the entire formula before you even begin. Anyway, if you negate it and convert it to clauses, you just get 2. And as I mentioned, if all of your clauses have at least 2 literals in them, you may have a problem. You will certainly need factoring. Now, possibly in this particular case, if you play your cards right, even without a non-trivial factoring, you may end up in a situation where you have identical literals which will collapse down trivially. But we can save ourselves a lot of trouble by factoring the clauses first thing. So we see here this PYY, PYA. If we apply a substitution, y goes to a, then we get PAA. Over here, the same thing happens. Once again, if we set the variable y to a, all of the y's become a's, the 2 literals become the same, and that is the result of factoring. In general, I should mention that you should keep the original clause as well as the factored version. The factored version, although shorter, is less general, and it's just possible that you might, in fact, need the general version. Not for this problem, however. We immediately see that there's a contradiction, so a single resolution step gives us the empty clause here. Here is something a little trickier. Now, again, I would love to be able to show you how you can look at such a formidable looking thing and write down all the clauses without any fuss. Because one thing you don't want to do is waste a lot of time covering half a page with squiggles in which you make a mistake on the 15th line and get everything wrong. So what you do here, I've told you before, when you negate a thing that has a bunch of stuff added together implies another thing, you take all of those things positively and convert them individually into clauses. Finally, you negate that thing on the right of the arrow and turn that negated thing into clauses. So we immediately get from this thing here, okay, we need to scolomize to get rid of that existential quantifier. So this will turn into P. Which one is this? It's that one over there. How ridiculous. Yes, not P or Q of A. I got thrown off for a moment. So this one here comes from there. You see the not P, because it's on the left side of an implies. There's our scolum variable. That should be A. I don't know why I put it over there. What else have we got? This will be some Q of B implies P, and that, for some reason, I put over here. Finally, what do we do with this? This, remember, we need to negate, so that will be for all x, not P, if and only if Q of x. And that is where we have these two things in the middle. So we have both of them coming from here now. Either P or QX is one possibility. Not P or not QX is the other possibility. So what do we do with these? And once again, we have many, many ways of combining these. You can kind of choose what you like, because as you can see, we have not PP, another not PP, but we also have not QQ, and well, that and that. Okay, and there are so many different ways of doing this, but I can see I have rearranged them in this order perhaps because I wanted to resolve these two together. So you see, there I have not q of b, there I have q of x, so I can unify those two. X goes to b, and the resulting thing here will be p, comma p, you see, which collapses down to p. Now I call this factoring because I've been talking about the factoring rule, although I suppose some would say it's not even factoring, it's simply trivial because that is a set. Then we see it, look at our clauses again and see what else we can derive. And here we see the not qx and the q of a. So they are complementary literals. And so then if we set x to be a, they are exactly complementary. We can resolve those two clauses and get not p comma p, which again, removing the duplicate, goes to simply not p, and then the result is trivial. Now, one concern of mine is that you get deceived by these trivial examples where, in particular, every clause is used. And imagine that real resolution problems look like these. Indeed, I know a number of students seem to think that the problem, or think that our task in resolution is somehow to involve all the clauses. It is definitely not. Real-world clauses will have huge numbers of irrelevant clauses, typically because our problem will be about a lot of different mathematical theories, and we will bring in all the axioms concerned with all of those theories, most of which will not be relevant to the proof at hand. And if you've got 1,000 axioms sitting around, you certainly don't want your resolution prover to start resolving them willy-nilly and using up all your memory doing nothing of any use. What you have got to do is ensure that your theorem prover stays focused on the actual contradiction it's trying to derive. One way of doing this is to somehow identify the clauses which were obtained by negating the thing you're trying to prove as distinct from the clauses that came from all the background theories that you had sitting around. This turns out to be still a big and important problem. And as we apply resolution theorem proving to more and more real-world problems, the issue of dealing with huge sets, very, very large sets of clauses becomes more pressing. I've said very little about equality in this course, mostly because it's difficult. In particular, for the Gensen type systems we've seen before, it's quite hard to do anything decent with equality. You can deal with equality in limited ways. For resolution, we have a complete proof procedure. So one approach is simply to throw axioms at the problem. So it turns out equality can be axiomatized in first-order logic. You simply put in the laws that's saying, like reflexivity, that is to say x equals x, symmetry and transitivity, they are easily expressed as clauses. Plus, for every function symbol f, let's assume it's a one-argument function, you put in clauses to say that f is, if you like, substitutive. All this says is that if x equals y, then fx equals fy, which of course we expect. Equally for predicates, this one says if x equals y and if px, then py. So if we throw in all of those axioms for every symbol we have in our language, you get equality reasoning simply by completeness, but the performance is terrible. To get something better, you need a rule such as the one here, which, by the way, is not on the exam. Paramodulation is pretty horrible. If you are finding difficulty getting to sleep some night, you might try to stare at this thing and see if you can figure out why it is true. Basically, this rule allows you to replace one occurrence of some term t, or an instance of it, t prime, unifiable with t, in some clause by something that it is equal to, and you see all the side literals get thrown in, and it's all a very complicated business. Don't let me be too negative, however. Such rules are implemented and they do perform well. It's just that you need to know what you're doing to implement such a thing if you're going to build your own theorem prover. If you're simply using a theorem prover, you can expect it to work in many cases. Now I'd like to move to Prolog, and we need to think historically. In fact, this course used to be called The Foundations of Logic Programming, and it was just these 8 lectures, of which this is the 8th right here. So way back in 1970, people saw that resolution was a complete proof procedure. They were very excited about it, and a number of senior figures in artificial intelligence, such as John McCarthy, the inventor of the Lisp language, thought that you could reduce all of artificial intelligence to theorem proving in first-order logic. And the idea then was that if you had any task that involved, say, planning of some sort, you could express it as a number of axioms describing, let's say, the capabilities of your robot, how it could move, its various appendages or whatever. And then you could simply prove a theorem to say that the robot is able to do this or to do that, and somehow the very act of proving the theorem would deliver a proof from which you could extract the actual plan for making the robot actually do what you wanted. This was a big fail. There are many reasons why it was a big fail, but at least one of them was that resolution did not perform well. It took up too much memory and it was too slow, and a lot of really very easy theorems were not getting proved. As one possible solution to this problem, people decided that the full resolution rule was simply too general and powerful, and that they should consider restricting it in one way or another, as such that you could then get a more efficient proof procedure. In particular, things called horn clauses were identified. We'll have a whole slide on them in a moment. But the point about horn clauses was they could be given a procedural interpretation so that the logic, the normal logic thing, P implies Q, had a procedural interpretation of to achieve Q, do P. And if it was P1 up to Pn implied Q, then you were meant to do P1 up to Pn and in that order. So it turned out they were able to get this very restricted form of resolution to run in an interpreter that it was still, in a formal sense, proving theorems, although you had fewer kinds of theorems were available because what you were allowed to write was restricted to these horn clauses. Nevertheless, in its pure form, it was theorem proving, and yet seen as a programming language, it could do a lot of cool things that could not be done in C, which already existed at the time, or even be done in Lisp, the AI language invented by Professor McCarthy. This in particular because Prolog used unification as its function calling principle. We'll see that in a moment. Of course, Prolog very quickly got contaminated, as Lisp did, by various hacks necessary to allow you to do computer-like things, such as do floating point or integer arithmetic, do input-output, or also if you want to hack your Prolog interpreter in various unholy ways, they were all thrown into Prolog as well. And here I've listed the names of the people who were the early pioneers in this work. So, what are these horn clauses? Very simply, a horn clause is a clause that has at most one positive literal. So in particular, it can have entirely negative literals. We write it like this. Now you see we use Kowalski notation for clauses. You're only allowed to have one of these negative clauses. It is called the goal clause. The other horn clauses have exactly one positive literal. They are called definite clauses. And as shown here, we have our procedural interpretation where to execute P, you execute A1 up to AM. And one of the crucial aspects of this restricted resolution is suddenly the order becomes critical. Before, clauses were sets. Now they're ordered. A1 must be done before A2, before A3, and so on. Finally, AM must be done. Moreover, your definite clauses, your program, is a list of clauses, and this list must itself be executed in order. So if you have multiple procedure bodies for the same procedure B, you have to consider them from left to right in your program if you see it as linearly, or from top to bottom if you see it as a normal program listing. Because of these strict rules on the ordering, it is suddenly possible to execute your Prolog program more like with a stack, whereas I'm not sure how clear it was in our previous examples, but in a general resolution proof, you just have a big collections of clauses that get bigger and bigger. You may remember from a couple of lectures ago, the active set and the passive set, possibly thousands and thousands of clauses just sitting around waiting to be used again. Whereas with Prolog, you have your program clauses, and they stay fixed forever, and you have your one goal clause. So this does change, and you have, I guess, some bookkeeping data structures, but that is it. The way Prolog actually executes is called linear resolution. You may recall from our previous examples that resolution can be pretty haphazard in the general case, where you have all of those clauses and you look at one for a literal that's complementary to a literal in some other clause fairly arbitrarily. With Prolog, all of that choice is eliminated. You have effectively no choice whatever, because at every point in execution, there is one single program clause you are looking at, and you are trying to resolve that particular program clause with your goal clause. And not just with any literal in the goal clause, but only with the first literal of the goal clause. So if the program clause doesn't match the first literal, you have to go to the next program clause, and so on. You keep going down until if you run out of program clauses, then you have failed, because you still have something left on the goal clause. If you are able to resolve a program clause with the goal clause, then the result of resolution, now this will be a normal resolution inference here, and it will produce a new goal clause with the negative literals of your program clause being put in front of the goal clause. So, as I've said, the program clauses will be attempted in order, and all the literals of a particular clause will also be tried in order. This will be a depth-first search, so whereas before, as I mentioned, we've just had kind of an iteration over clauses using more and more memory. Here we're using a stack and depth-first search, and in particular, if you reach a dead end, you can always go back and see if you could do something differently using a different program clause and get a different result. Finally, and a rather big restriction of Prolog, is it does not do the occurs check in unification. The reason is that unification is the basic parameter passing mechanism of Prolog. And the occurs check basically involves examining the entire parameter being passed, which could be a very large expression, to see whether or not it contains an occurrence of the exact parameter name that it is being unified with. And I guess the idea is that in practice that would not happen very often, and the cost of doing these checks would be prohibitive. Nevertheless, you can occasionally get, because of the check not being done, you can get infinite loops during unification itself, or cyclic data structures being created, which of course should not be. And this is just one of those little hazards involved in using Prolog. Now here is a program I wrote about a family I know. Now if you recognize these names at all, you will have an idea how long ago it was that I made this slide, when some of the people on this slide were actually very young indeed. But never mind that, this is a typical example of the things you can do with Prolog very simply. So as you see here, we have three relation symbols, that is to say parent, grand for grandparent, and cousin. We put in some facts, so a statement in Prolog which is just a unit clause, especially if it is a ground unit clause, so no variables, it is called a fact. So this fact is Elizabeth is parent of Charles, and this one, Elizabeth, parent of Andrew, although possibly she wishes she weren't. Charles, parent of William, Charles, parent of Henry. And finally, Andrew, parent of Beatrice, and Andrew, parent of Eugenia. So we have 6 facts. Now this so far is pretty boring, but we can do some interesting things with these. So we can now define the grandparent relation, and rather than listing the grandparent relations explicitly, we give a way of calculating it. So we say X is the grandparent of Z if X is a parent of Y and Y is a parent of Z. And you see Y is not bound here. So we are not restricting Y in any way. For X to be the grandparent of Z, it is enough for there to be some Y that lies between them, so to speak. A similar thing happening here with the cousin relation. For X and Y to be cousins, it is sufficient for there to be some Z, otherwise unconstrained, that is the grandparent of both X and Y. So we can execute this, and again I do wish I had a second projector, but you just have to imagine me going through this. Maybe take a look at this slide, fix it on your screen and look at it while I go through this execution here. So a typical Prolog execution begins with something you might call it a query that we ask the Prolog system. So you say solve effectively by writing it like this, cousin xy. So this is a negative clause, which is to say it is a goal clause. And that means we are asking the Prolog system to solve this goal. And in the course of solving the goal, because I mentioned once that in Prolog, and indeed in resolution theorem provers, variables are things that begin with capital letters. Things with lowercase letters are constants, and that is why Elizabeth, for example, begins with a lowercase e. Okay, then, we want to show that x is cousin of y. We don't even know what x and y are. And the various answers returned by the Prolog system will be, so it's not only proving the theorem, but it is also creating instances of the theorem at the same time, and therefore answering questions for us. Now, the way this will be solved, remember, starting here, is to go down the list of clauses until it finds one that matches the cousin relation. And incidentally, we don't really go down the list of program clauses. We have clever indexing mechanisms that will lead us directly to the relevant program clauses and do all the right things efficiently. The relevant clause will say you have the XY relation between cousins, you have the cousin relation between X and Y, provided there is some Z that is a grandparent of them both. And you'll note that I did my renaming variables apart here. So instead of calling it Z, I called it Z1. That's what the Prolog system would do. It would generate a new variable name. And by the way, that new variable name would be a good deal uglier than Z1. So now our task of showing that x and y are cousins has been replaced by the two tasks of showing two grandparent relations with the same grandparent. Going down the list of program clauses again, we find only one way of solving the grandparent relation, which is to create two parent relations. And you will note how now two new variables have been introduced into our problem. So we still have the original x and y, but we also have z1 and y2. They were introduced in the search process. So to solve this, we have to solve all three goals, and crucially, they have to be solved in the order given. First that one, the parent z1, y2, then this one, parent y2x, and only at the end, this other grandparent goal. So now we go through our list of clauses to find something that unifies with parent z1 and y2. They are both variables, and so any of the parent facts will solve this goal. So in particular then, Z1 can be Elizabeth and Y2 can be Charles. The result of this unification will be to delete this literal. So here we had three literals, but because we can unify this with a fact, we end up with two literals, and you can see now that Charles has been plugged in for Y2 and Elizabeth has been plugged in for Z1. What happens now? We have a parent thing to solve again. We again go to our program clauses and we find parent Charles William, and that now sets x to William and gives us the problem of Elizabeth being a grandparent of y. Now you might ask, what is the asterisk doing here? The asterisk indicates a choice point. So I chose parent Elizabeth Charles, but there were many other things I could have chosen. I could have chosen, in fact, parent Charles William here, but that would have given me a dead end because, in fact, Charles is not, at the time when I made these slides, and therefore the time that is described by these slides, Charles was not a grandparent, and so there would be a dead end. The search attempts would eventually fail, and it would have to go back to this choice point and make another choice here. But of course, Elizabeth William, which is the choice we made, is going to work. Now, where are we now? We are at parent Charles X. X will become William, and we have grandparent Elizabeth Y to solve. Going through our program clauses again, there's only one way to solve a grandparent relation, which is to solve the two parent relations. And I hope it's clear, by the way, that this is simply a standard resolution here, where this negative occurrence of grand is resolved against the positive occurrence of grand in the program. So they cancel out, and we are left with the corresponding instances of the other literals in that program clause. Now I'm going to cheat a bit. As I mentioned long ago, the problem with the definition of cousin that I gave is that it says that you are your own cousin, and moreover, that your brother is also your cousin. Nobody really wants that. So I'm pretending in this execution that somehow we have backtracked until this time when we solved for parent Elizabeth something. Instead of choosing the first choice, which is Charles, we chose the second choice, which is Andrew. In fact, I think Andrew is a lot worse than the second choice. So we finally have to show parent Andrew something, and the first choice that will come up for that is Beatrice. And we have now proved the original theorem. Or you could put it this way, because the original theorem is, I guess, to show that there exists an x and y such that cousin xy. When you negate it, you get this effectively says for all xy, not cousin xy. Excuse me. Having refuted that negative clause, we end up proving that there exists a pair of cousins, and there they are, William and Beatrice. So this is how Prolog systems work in practice, and if you're doing it interactively, you can indeed force Prolog to backtrack and give you other options. Under program control, backtracking will happen naturally if you make a choice that leads to a dead end later in execution. The system will automatically go back and revisit another choice. What is it good for? Well, as we've just seen, you can throw in a lot of facts and some abstract concepts relating those facts and immediately get the ability to not only retrieve the facts you have just plugged in, and it might do it quite efficiently, but also to make simple deductions such as about cousin relationships or anything else of that sort. A really cool application that goes right back to the earliest days, 1970 or so, are so-called definite clause grammars. These are ways of coding grammars for natural languages in a thing that looks like normal grammar rules, and it can be translated in a systematic, indeed in an automatic way, into Prolog code, to which you can attach further Prolog code to give you well, I'm about to say semantics, but not semantics in an abstract sense, but shall we say a pragmatic interpretation of whatever syntax you just put in. So Prolog is very good for natural language applications, but also at the time this emerged, I said it in the 1970 or so, there was a lot of interest in robot planning, and things like specialized languages like Planner existed that also had this backtracking control structure. But the backtracking is more natural, more logically based in Prolog. People went mad about Prolog, although now I think people are not so excited anymore, just as Lisp has kind of faded from the scene. But we are not quite finished with Prolog yet. So there is a way of doing full first order logic in the Prolog style. So let's imagine now we are not programming anymore. We're back to proving theorems again. And we have got a whole bunch of clauses that arose from negating some conjecture, and we want to prove our theorem. Well, instead of using the normal resolution calculus, we can do it in the Prolog way. One trick to doing this is not the only way, but one trick is to say, if I have an M literal clause, I can turn it into a set of Prolog clauses. The key feature of a Prolog clause is that one distinguished literal, which is called the head, is, well, it's distinguished. It is set aside, and it is the only one that is matched against another literal. So if you turn this single M literal clause into M different clauses, and you see these clauses are all logically equivalent, all we are doing is using the negation symbol to give, if you like, priority to one of the M literals. But in every case, the meaning is the same. The meaning of every one of these clauses is this disjunction A1 or A2 up to or AM. Now it turns out I guess you need to have a negative clause here to start the thing off. If you don't have a fully negative clause, incidentally, then your set of clauses is satisfiable. Because if you don't have a negative clause, that is where all the literals are negative, then you just make all the predicate symbols always true, and you will satisfy your clauses. That was a little aside. Anyway, you choose a negative clause to be your goal clause, and then you can do resolution. There was one further thing we need in order to make this complete for first order logic. It's a little obscure, but let me just mention it. Every time in this system here, you set up P as the goal you are proving at the moment, temporarily add not P as a fact that is available to you. This gives you a kind of proof by contradiction principle, and if this is added into your system, you will have a complete procedure for first order logic. Now, why should we bother with this if we have proper resolution? That's a good question, and today's resolution provers, which do not use this principle, are very powerful. There was a time when this was in vogue in order to take advantage of very fast Prolog machines that were being built. I'm not sure ever in hardware, but certainly very fast Prolog software architectures were being built, and you could get a very high inference rate using this technique. But the techniques shown on this slide have been generalized into what is called the connection tableau method, which we're not really going to cover here, but you will certainly hear about this method if you continue in this field of automated theorem proving. So, looking at theorem provers that have been built, Now here we're going kind of into the dark ages. So it was around in the early 90s when people were building theorem provers directly based on the reduction to Prolog thing I showed you on the previous slide. These are extinct now, though they were cool in their time. Even today, there is the connection calculus, which has emerged from the model elimination techniques, and there are some systems that use that. There are various other systems here based on higher order logic, based on the sequent calculus, but the big ones, the big full-scale resolution theorem provers, are these here. They actually haven't changed. So in all the years of doing theorem proving, going back at least 2 decades, these have been the big three. You can find them online. Certainly the first two you can download without any fuss at all and build them on your laptop tonight.